Okay. Okay, so we can talk about something. How many of you, especially, or any of you, well, some of you are like physics junkies, I know this, or physics majors. How many of you have ever seen tensors used? Right? Right, like Einstein, I mean, they said relativity, right?
And also, yeah,
Right. So we're gonna do the real tensor. I want to go through this section, rather quickly, just I want to give you kind of a big picture detail. But a tensor product of modules is another one of these universal mapping kind of things, right? Like the direct product, the direct sum, there are solutions to certain problems. And the problems that tensor products solve as far as making diagrams commute are with maps that are called bilinear. And every time I talk about this, I feel like I'm doing Calc 3 in a certain sense, because that's essentially what bilinear maps are. Oh, by the way, this is 12.8. Well, that was strange. You'll get my email at your office hours today, right? I'm gonna cut them off, and then if it's all free, just give me a holler. But A, B, and C, D are modules. A map from A cross B to C is bilinear. Well, yeah, from A cross B, C is bilinear if for all A, AI, and A, B, BI, and B, we have one F of A1 plus A2 comma B two F of A B1 plus B2 is F of A B1 F of A2 and 3 here I'm going to assume that ours community running, these are all modules. You can do the tensor product with left and right modules, but it's more complicated. So what it needs to be bilinear is, and this is why I think that I'm teaching Calc 3, is if you hold B constant, then it's in the first variable, it's basically, it's a homomorphism of bin groups. And it also does this R module business. So it's an R module homomorphism if you freeze the B. And if you freeze the first coordinate, it's an R module homomorphism in the second coordinate, right? So bilinear just means that it's linear when you freeze on the variables, which it reminds me of setting up for partial derivatives. Now, this is a bilinear map, and I'm going to jump right into it. This is the general construction of the tensor product, which you will probably not see in your physics book. Definition. 12.8.2. Let A, B, and C, or A and B be R modules, and F3 of the, okay. And F, free abelian group on the Cartesian product A cross B. So in other words, you consider every distinct element of A cross B, any little a comma B, as one of your basis elements in the free abelian group. So this is basically consider everything in A cross B as just an abstract symbol, and let that generate some free Z module. That's what you're doing there, right? but we're not gonna leave it at that. We're gonna crush out by a bunch of relations here. Let K be the subgroup of F. So this is, look, this is gonna look like big pile high gravity, right? Very confusing. I'm gonna show you what this is, and then I'm gonna show you how to manipulate and the manipulation stuff. But maybe the subgroup of F generated by all elements of the form. And this might look familiar when I do this. A1 plus A2, comma B, minus A1, comma B, minus A2, comma B. 2 and RAB. So in the quotient group, if you have coset representatives, what should be the case in the quotient group is A1 plus A2, comma B should be in the quotient group, A1, comma B plus A2, comma B. And A, comma B1 plus B2 in the quotient group should be this plus this. If you take these to be the coset representatives, and these two should be the same in the quotient. This probably rings familiar with regard to this. We define the tensor product A and B be F mod K. Let me give you some notation. In this group, so this is of course pre-abelian group modulo these relations here, right? So you've picked up also the relations to the original modules A and B. In this group, the coset is written tensor here. This is just a notation. It's a shorthand for whatever this coset is, and it's called a tensor. So let me put a mark here. All right. Notice the inclusion map. I should say inclusion. The inclusion map, iota A cross B into A tensor B, given by what I think you think it would be. Iota of the ordered pair AB equals A tensor B is a bilinear map. All right. So I'll check the R in one variable, of course. Notice that if you do iota of A1 plus A2, comma B, this is A1 plus A2 tensor B. right? That's the way this is defined, right? And let's look, I guess, really, this is relation this. What this means here, this translates to, and these are the basic rules of messing with tensors. This translates to in the tensor product, A1 tensor A2 plus B, I'm sorry. A1 plus A2 tensor B is equal to A1 tensor B plus A2 tensor B. This rule of the tensor product translates to A tensor B1 plus B2 is A tensor B1 plus A tensor B2. And this translates to RA tensor B equals A tensor RB. So if we look back here, this is A1 tensor B plus A2 tensor B, which is iota A1B plus iota A2B. Everybody here with me? And for example, iota of R A B is R A tensor B, which is A tensor RB, which is iota A RB. So you can move things across the tensor. Basically, so the workaday mathematician, A tensor B. What is A tensor B? Well, it's just I wish I could say it was just a collection of tensors. Unfortunately, that's not going to pan out for us. It's actually sums of tensors. Finite sums. So a typical element of this is just a sum of tensors. And it's subject to the following relations. One, you can simplify these things along any of these lines. A tensor B1 plus B2 and 3. And here I can put some more talk about our module. So any of these relations work. So it's something that where you can manipulate things like this. In a tensor product, so I want to do some computations. If you ever tensor anything with 0, you get 0. Right, that's the 0 element of this, right? For example, let's do this. Uh, I'm not gonna, we're gonna take a guess at this, because I'm gonna need to give you a theorem, to make sure that it's right, but let's see if we can kind of guess. Let's write Z in this way. What does a typical element of this look like? Well, write this out. N1 tensor K1 bar to the tensor K2 bar and some M tensor K some M bar. That's what a typical element looks like. I might agree with that. But this one is groovy because you can actually write everything in here as a single tensor. Anybody see how? Right, it's not really clear from these, how you're gonna get this all together, but one thing you can do is slide stuff across the tensor, right? We can assume no Ni is 0. So if alpha is not 0, so certainly alpha could be 0, but if it's not 0, we can assume that no Ni is 0, because if one Ni is 0, it drops out. Well, I might as well not put it there in the first place, right? In this case, I can slide every integer across the tensor. Right? Because remember, of course, Cn is a C module, and so multiplying elements of Cn by integers makes sense, right? I agree with that. Now do you see how to put this into a single tensor? These ones in the first coordinate are all the same. So I guess I could use this rule with several things applied. This is actually equal to one tensor sum of Ni Ki bar I equals 1 to M. So in other words, everything in here can be written in the form one tensor something, right? Not just a single tensor, but one tensor something. And in fact, even 0 can be written as one tensor something, as one tensor 0 bar. All right, everybody agree with that? Anybody want to guess? But just sort of by analogy, can you guess what this is isomorphic to? It's Zn, right? Because really, every element looks like one tensor something, and you just vary through the elements of Zn. Now that's really sloppy, and we're going to show that this, in fact, actually is isomorphic to Zn with use of the theorem later. Here's something that's quite useful in, like, for example, topology and some other things. I like to say tensoring with. So check this out. Example, but P the torsion view. And what I mean by torsion is T might be an infinite group, but every element of T has finite order. Right? That's what it means in torsion. Every element has finite order. Okay with that? So of course, T is a C module. What happens when I tensor this with rational numbers? guess on this? Actually, let's just look at a single tensor. I claim that tensor is C. Let's see how to do it. What's it? What do I know about T? The T part of that. Well, I know it's got finite order. Do I agree with that? Since the order of T, suppose the order of T is N, right? Then N times T is zero. So if I add T, excuse me, to itself, N times it is zero, right? Now watch. So, I feel so dirty doing this. So, T tensor Q is equal to T tensor right? You gotta love them rational numbers. Nothing up there. But see, now I can take this N and slide it across the tensor because we're tensoring over C. And this is NT tensor Q over N. But this is zero. So what we've shown is every single tensor is zero, but the tensor product is generated by all the single tensors. So I'm generating this with a bunch of zeros. So this is zero. I've heard all of us say it all the time. Ooh, tensoring with Q kills torsion. And that's what it does. It wipes out all the elements of finite order. In fact, this is a tool sometimes if you have some general abelian group and you tensor with Q, then it tends to sweep through and kill everything in finite order. Yes.
Do you need Q or do you just need any divisible abelian?
Yeah. Q is in a certain no, I don't divisible.
Like when you're working.
Yeah. Divisible will work. Yeah. Divisible work. But Q is in a certain sense more efficient. Right. Okay, other questions? All right. So there's a couple of examples. So I hate to do it this way, right? But really, you can think of the tensor product as just this kind of orgy of symbols that you sum up, and you've got some rules that allow you to manipulate it, right? And that's it. One of the difficult parts of this, one of the most difficult things about tensor products is if I walk up to you and I give you this, or sometimes even a single tensor and say, is that zero or is it not? Sometimes it's hard to tell. But we have some tools here that we're going to develop that will help us. And this is kind of where the tensor product comes from. I did say this business about the solution to a universal mapping problem. And here's where the tensor product fits in. Here, if A, B, and C are R modules, and G from A cross B, C, a bilinear map. then there is a unique R module homomorphism. The R module. Call it G bar from the tensor product in C, such that we're going to do iota G bar. This is G. So here's our situation here. So this seems like this is actually, I think, one of the most useful things when you get down to it. Here, this map iota here, this takes the ordered pair AB into A tensor B. So it takes the ordered pair AB into a single tensor A tensor B. If you have a bilinear map from here to here, this gives rise to an R module homomorphism here to here that makes the diagram commute. And not only that, the tensor product is unique up to isomorphism. Uniquely up to isomorphism. And I actually, at the end of this, when I'm finally done with all this abstract nonsense, I'll talk about vector spaces too. Because the tensor product over vector spaces, which is what Einstein, I think, is it's a lot more easy going. And in fact, I'm going to prove one thing that makes this kind of nice. Okay, yes.
When you say, like, what does determined mean again? Like,
It means if you have any other R module that satisfies this mapping property, it's isomorphic to the tensor product.
Okay.
Right, that's what I mean. Okay. At first, this seems like, okay, just another one, but I think that this one is more powerful than a lot of the other ones, and I'll tell you why. Can somebody tell me why, if I just walked up to you on the street and said, hey, look what I got. I've got A tensor B, and I've got this other thing C, and I want you just to build an R module homomorphism. That's my project for you today, is I've got A tensor B, and I want you to build an R module homomorphism. See, can somebody tell me what's going to be nasty about this right out of the gate? Yes.
RAB is the same as B or A RB.
Is there something more general you could say? What is a typical element of this look like? Sum of tensors, right? Well, what is a tensor?
Coset.
It's a coset. And what's the problem with that?
Well defined.
That's right. I mean, if I just walked up to you on the street and did this, all of a sudden you've got to think, okay, what the heck? A tensor B, look, it looks all nice, but that's really a coset. And there's many, many ways to represent A tensor B. You might be able to write some other C tensor D, blah, blah, blah. Question one right out of the gate. Is this even a function? Is it even well defined? And that's going to be a pain in the butt, right? This is the magic of this. If you could just take the pieces A, B, and find a freaking bilinear map to here. And bilinear, there's no cosets here, right? You don't have to worry about that in the first place. And bilinear, much easier usually to determine. Any bilinear map, you spray a little fertilizer on it, and it grows up to an R module homomorphism. So this theorem actually does some really heavy lifting. It allows us to take really kind of an easier thing to determine and say, hey, then I've got an orthogonal homomorphism basis for it. Now, I don't think I'm gonna prove this theorem for you because it's actually not too difficult, but it's just rolling around with the symbols. But I am gonna use it. So here's an example, and this generalizes my first example where we did Z tensor Z with Zn is isomorphic to Zn, or at least so we thought. By the way, it doesn't matter in the case that we're looking at in community rings. M tensor R of R is the same thing as R tensor M. It's the same, it doesn't matter what order you do it in, see if you can prove that.
So would that mean like A tensor B is the same as B tensor A?
Yes, that's right. Yeah, in fact, I think actually, see if you can prove that A tensor B is isomorphic to B tensor A, and the ideas are all in what we're going to do. So let's show this. I want to build a homomorphism from here to here, but again, out of the gate, what is even a single tensor? A single tensor is a coset. Who knows, right? What I can do. To all. Not sorry to him. Anybody think of a bilinear map? A way to take this ordered pair, shove it into M? Or easy, right? I mean, that's kind of the most natural thing to do. Let's hope it works. But that's the great thing to do. All we gotta do is check this bilinear, and that's and I'll call this G, and that's not too bad to do. Notice that G of M1 plus M2, comma R, is R M1 plus M2, which is R M1 plus R M2, which is G M1 R plus G M2 R. Right. G of M R1 plus R2 is R1 plus R2 M, which is R1M plus R2M, which is G of M R1 plus G of M R2. I agree. And finally, here T is in R. This is TMR. Oh, I guess it's RTM, which is G of M RT. So it's bilinear. This means well, in this case, I guess it's M tensor R. This is ours. And there we go, we've got our module homeworks, yes.
It doesn't matter that it's RT instead of TR, like.
No,
the
because I'm
range
assuming my
conversion.
research community.
Oh, okay.
Yeah. But yeah, you bring up an important point, because actually to do the tensor product in the non-commutative case, you need A to be a right module, B to be a left module. And yeah, because the tensor goes, AR goes to RB, yeah, I don't even know all that stuff. Okay, other questions? Yes.
So, did we show that this tensor product is an R model?
No, not yet, but it's an abelian group for sure, right? But the R action is as I described, but it's easy to verify. Your R times the tensor A, R times A tensor B
Mhm.
is RA tensor B or A tensor RB.
And so there's just a relation that, like a,
If you define the R action to be that, it's an R module, and that's easy to verify. Other questions? Okay, so the magic is done. I never have to worry about well-defined in this. I didn't have to worry about the R module homomorphism bit. That is just done by the theorem for us. What I do have to worry about is isomorphism. Yes.
is there a name for 12.8.3? Is like a universal mapping?
This is the universal mapping problem, potential product, something like that. Okay, well, I guess it's clearly on to, isn't it? Because if M is in M, you might think of something that goes to it.
In common point.
Is that right? So if you would do chief R, which way to do it? M tensor one R. This is M, right? And it just follows from the diagram commuting, right? Because the M comma one here goes to M tensor one R. And up here it goes to M, and so since the diagram commutes, there we go. The one-to-one is a little bit more delicate, but it's not too bad, and we're greatly aided by the fact that in this particular tensor, product, you can write everything as one times a tensor. So note n, so I'm going to make this simple first. N tensor R, every element is a single tensor. Of form. And this is going to help us, right? Yes.
Well, we have to assume that M is unitary.
Yes, we're making that assumption. Okay, so let's prove this. Okay, so 0 tensor one R is the element, so there would be written as well. Well, it says this way, a non-zero can be written M1 tensor R1 plus M2 tensor R2 plus MK tensor RK, where RI, none of the RIs are zero, because if any of the RIs are zero, I'm just going to put them in the representation. And this is M1 R1 tensor one, M2 R2 tensor two, or tensor one, plus MK RK tensor one, which is the sum of RIMI tensor one, which is M tensor one. So everything in this tensor product can actually be written in this special form. Okay, so let's suppose alpha is in the kernel of G bar. Well, by my observation over here, M alpha can be written in this form, right? Everybody agree with it? So here's what I've got. Now, if this goes to the over here to 0, because I'm assuming it's in the kernel, right? Then that means that and so here, there's your unitary part right there. 1 times m equals 0 means that m is 0. Right? Therefore, G bar is 1 to 1. And that does it. Right, okay.
So did we show that G bar was the isomorphism?
Yeah,
G
that's
bar is
right.
isomorphism.
Yeah. What we didn't have to show by this theorem was the fact that G bar is a well-defined function that's also an R module homomorphism. Right? So that's a bunch of crap that we would have had to do ordinarily that we didn't have to do because of this big theorem. Any guesses? This one? Well, I guess that. What do you hope for? That's right. You've been good this year. Maybe Santa Claus will let this be true. And the fact it is. So, and actually it's true on the other side. So if I look at B sum C tensor A, right? So this distributes just like multiplication and addition in a certain sense, right? See if you can prove this, right? Set up a diagram. You do something. So I guess what we need is yeah, we might need something like that. Maybe there's a better way to do it. Anyway, see if you can do this, but the upshot is that's another property of, uh. Yes. It's a product. So it behaves well, it distributes across direct sum. And it's also true that when you tensor something with R. So let me ask you this, given what we've had, and by the way, I didn't tell you this, but that works with any direct sum, not just the direct sum of two things. But in general, it's true that the direct or the tensor product with the direct sum of BI is isomorphic. Yes,
Does the direction have to be finite?
no, it doesn't. Yeah, that's a great question, but no, it doesn't. So, so here's kind of the last takeaway that we'll do today. Suppose that was a free module. And of course, we know what a free module is, right? It's just some number of copies of R, and this is uniquely determined by how many copies are on. So F is isomorphic to the direct sum of R. And once you know how big the index set is, that's all you need to know. What happens when you take F tensor some module A? Well, this thing is the direct sum right? Well, by this previous theorem, we can commute direct sum, it's a product. Right? But this thing is isomorphic to A. So this is isomorphic to so when you tensor a free module with A, it just barfs out a whole bunch of copies of A. How many copies, you may ask? Well, as many as there are elements in the basis of F. Yes.
So does F tensor A become a free A module?
No. A is module. Right. It's
Okay.
not A. Yeah, it's just the appropriate number of copies of A, and the number of copies are however big the basis for F is. Right. We'll talk more about this next time. Any questions? Yes.
If we had a ring as Z and let's say you have like instead of A you have R, like the real numbers, then does F tensor the real numbers become a free, like a vector space?
No, because we're talking about modules over Z.
Right.
Right. So it's that's potatoes and tomatoes there. Right? Okay, other question.
Is that, like the second line, is that isomorphic to the third line? Or is that equal? Like, is that the?
Oh, no, I was starting to set up a diagram here.
Oh, okay.
Like this was, I didn't even draw any arrows or anything, but I said you might see if you can set up a diagram to try to do this. Okay, others? All right, well, I'll pitch you folks on quick.